So we will start. We are already late. So today's topic is this one: design concepts of single dish telescopes and phased arrays. And this is your 7th lecture out of 13. And this is something about what we are going to talk today. Like I'll just read this one. In the last few lectures, we have studied about the basics of antennas. In this lecture, we shall study the design considerations of single dish radio telescopes and construction of arrays. We aim to cover the topics of field aperture radio telescopes. We start with the angular resolution of a telescope, and this is described by Rayleigh criterion. I think some of you may be already knowing this one, but I will again go through this one. And then we move on to the design of single dish radio telescopes and aperture synthesis. We shall talk also about phased antenna arrays. And in the process, I will also show some of the techniques for designing a different type of antenna feeds. Only very few antenna feeds I will talk about, not all. So we begin with the Rayleigh criterion. Now you see this is a lens, and this is the focal length of the lens. This is a screen here, and if there is an object like a star or a point object emitting light at a single frequency, that is monochromatic, then you can focus that object on the screen here. Now it should look like exactly like the star or whatever you are pointing to, that point. But then in reality it doesn't look like a point here. It appears to be a spread out function, and that is why it is known as the point spread function. So here you can see this is x and y. This the screen is on the x and y, and you are observing along z direction, and intensity is maximum along that direction, and then it falls down and it forms a pattern like this. So this when you do it with a lens, you will not be able to see it, but if you increase the intensity and all, then you can see this one. And also you cannot do it on objects like stars and all with a lens, because they are not monochromatic. They have a band of frequencies. Monochromatic, by monochromatic I mean that it should have a single frequency. So in 2 dimension, this looks like this. So this D is the diameter of this lens, and F is the focal length of this lens, and lambda is the wavelength. So if you just scale it down, you will see that when this value is unity, at that point, this is the minima, first minima, that is occurring at plus minus 1. Then second minima plus minus 2, and so on. Now, if you want to observe another object like a point using this system, you will be distinguished between the two, provided they do not overlap each other. Not overlap each other, they can overlap, but they have to be certain distance apart in this plane. Somewhere it should be. So the best position is that it should be at the minima of the this one. Where this intensity of the first object is minima, there the maxima of the second object will be there. And this distance, or in angular distance, if you calculate it in this, then it comes to around 1.22 lambda by t. So this is what is Rayleigh criterion. 2 monochromatic point sources at same wavelength can be resolved with a single telescope if the angular separation between the 2 objects is at least equal to or greater than alpha dash, as expressed below. So alpha dash is the minimum angular resolution. That's maximum angular. I don't know how you say it, but this is the angle. If the 2 objects make an angle less than this, then you will not be able to see it as 2 on the screen. You will be seeing it as 1. So I will go into more details in the next page. And here are the definitions. Lambda is wavelength, d is aperture diameter, this one. In case of a telescope, it will be the diameter of a telescope. Alpha dash is the minimum angle between the 2 points in radians. So this value comes out in radians, and lambda and d are in same are having same dimensions. So, and also you can approximate it as lambda by d. And this is what you may be hearing many people talking about, the resolution of a dish is lambda by d and all. This is where it comes from. Actually, it should be 1.22 lambda by d. Now you see it in more details here, what I was talking about in earlier page. So here you see that this is the lens. Now from here, this is the first, there are 2 stars separated by an angular distance. You can see between these 2 there is an angle. That is the angular separation between the 2, and they are monochromatic and having the same wavelength. So this is the light from star 1 and this is the light from star 2. Naturally, you will see 2 point spread functions formed at these 2 locations. One here for star 1 and one here for star 2. So this, when you see it here, if you plot it, you will see that this is for one and this for another. And if the distance between the 2 reduces, then these 2 will come very closer. These 2 peaks will come very closer. And effectively what you will see is this envelope, this dotted line envelope. So they will merge. So you will not be able to see it. You will not be able to resolve these 2. So ideally this should be here or beyond this. The reflection pattern is a function of wavelength. Thus only monochromatic light is assumed for setting Rayleigh criterion. If the frequency bandwidth is increased, spread functions will result for each wavelength and the image will be blurred out. So if you have multiple frequencies, if you have a band of frequencies, then there will be many such point spread functions of different widths, and so ultimately what you get is a blurred out thing. Then we show what are the components of a dish antenna. This is where you place the antenna feed, and this is your dish, which is steerable. It lies on, you can rotate it in azimuth and elevation. Some arrangement is here, and this is the radiation pattern of this antenna feed, which is illuminating this dish area, and this is the effective beam pattern combined with the feed and that of the dish. So this is a combined one. And here is a distant radio source, and so we assume that on the surface of a dish, we assume the rays are plane waves. So the wave fronts are flat. Now there are different sort of arrangements which you can place here, or this entire arrangement. This can be having a different types can be used here. For example, you see this one. This is called the Cassegrain arrangement, in which the antenna feed is located here. There is a hole here, and there is a sub-reflector here. So the rays come here, it gets reflected back and comes down here. So this is also this is very popular in optical telescopes. They use this one, but in radio telescopes also they use it. There are certain advantages and disadvantages for all of this. In this case, this is called the Gregorian arrangement. In this, instead of the radius of curvature is just opposite here. Here, this is the sub-reflector. You correct your feed is here. There is a hole here. Then this is off-centered. This you might be seeing in the dishes what you use for your television, this DTH and all. You will see there is an off-centered arrangement. The feed is kept slightly away from the dish. So this is the off-centered arrangement that is used here. So this has got many advantages, but again, all of them has got advantages and disadvantages. and this is a paraboloid arrangement. This is the one of the simplest one, where you have the exactly something like this arrangement, exactly something like this. You have a feed here, and this is your paraboloid dish. Then we go for dish aperture illumination by feed. Now, you know from the reciprocity theorem that the transmission and reception properties of an antenna are identical. So sometimes in this lecture we will talk about the feed to be illuminating the dish. That means it is transmitting, and sometimes we will use the feed as a reception kind of terminology we will use. But all it means, the properties what we talk about remains same for both of them. This is for our convenience we are talking. Now here we are thinking that the antenna feed is located here, and which actually illuminates the dish. That means the feed pattern has to be something like this. So you want to uniformly illuminate the dish. So every area of the dish you should receive same flux density from the feed. But outside the dish you should not have anything. So this is called ideal illumination. But then there are certain drawbacks of this. That there is a discontinuity here. Suddenly the illumination comes to zero. And if you take the response of the dish with the entire system response, or the radiation pattern of this system, you will see that there is a major lobe that has to be there, but combined with many side lobes which are having very high amplitude. So here is the record, and an ideal antenna feed is capable of illuminating the aperture of the dish uniformly. It's ideal. In practically you cannot make such things. And the side effects are huge side lobes are generated due to discontinuity at the edge of the dish. Now here is something more of a practical kind of thing. Here you see that you have a antenna feed which is having a radiation pattern something like this. It is having side lobes and back lobes, and also it does not uniformly illuminate the feed, because here at this point the illumination will be maximum, because the feed will have maximum directivity. This is the directivity along this direction, or gain along this direction will be maximum for the feed. But as you go away from this, you will see that it reduces. So what will happen? These areas around this will be less illuminated than what you have at the center. Then due to the side lobes, you will see that some radiation will be going outside. I am just talking about, now I am talking in the radiation mode. I am telling that this feed is radiating. It's same thing. When you receive it, it will receive in this same direction. So right now let us talk about radiating properties. So what will happen is, from the side lobes it will catch a signal within this angle. From this side lobe it will catch within this angle. From the back lobe it will catch within this angle, and so on. And also if the dish is made up of a mesh, something like JMRT, depending on the frequency, you will see that some portion of this illumination will be leaking through. So that part will be lost. So ultimately what you will see is, this will be the sort of response where you see the back lobes are back lobes and side lobes are much smaller as compared to this ideal illumination case here. But the drawbacks are, there will be certain kind of effects that is happening. Now this is called spillover. Spillover is this main beam of the antenna feed which extends out of the dish. So that region will pick up something from outside the dish. So this is called the spillover area, this one and this one. And these are the side lobes, because these are picked from the side lobes. Again, this is another side lobe, and this is the back lobe pickup. And this is the illumination leakage. So this diagram one should never forget, because this is what is happening in most of the dishes of radio telescope. And also the illumination leakage increases with the frequencies, because the actually the net what you are using in any antenna should be at least 20 times lower than 20 times of less than the wavelength. That is lambda by 20. The dimensions of the mesh should be less than or equal to lambda by 20. Then only you will get some 95 and above percentage to be reflected back. Leakage will be very less. So that is another reason why you will see that GMRT 1420 megahertz has not very good, I mean mesh leakage is very bad there. So I will just read it if I miss something. Actual antenna feed pattern produces a non-uniform illumination of the dish. So this is non-uniform because, as I said, that at the sides you have lesser power in this area, and here it will be more. So the the illumination across the dish will be non-uniform. The side effects are these are the things what I explained: spillover, then minor lobe pickup from different directions, and dish may possess some illumination leakage. This is the illumination leakage. Combined pattern has side lobes and back lobes. You cannot avoid these side lobes and back lobes. Only you can do is to, at the best, how much you can reduce them. You can never make an antenna practically which is without any side lobes. Now we have studied in engineering. People might have studied that the effective area of a dish is something like 0.4 times its actual area, 0.4 to 0.5 times. That is pi d square by 4 into something, some constant which is less than 0.5, 0.4 to 0.5. So what is that actually? That is the antenna efficiency, or not antenna efficiency. It is the aperture efficiency. It's called the aperture efficiency. Now, aperture efficiency is calculated from these things what I explained, and they consist of the product of these particular things. So there are 6 major factors affecting the performance of the dish antenna system, which are efficiency of the antenna feed. That is, the antenna efficiency. That is R divided by RL plus RR. We will discuss about this. I'll give you slightly more details. Then spill over efficiency. That is the efficiency getting lowered because of this spillover. These definitions I will give you in the next page. Then dish leakage efficiency. That is mesh depends on the quality of the mesh. So quality means how small is the hole of the dish. That will decide its quality, and this relates to this one. It's a eta mesh, and then surface smoothness efficiency, eta RMS. So now you also know that the dish can never be, when you make a practical dish, you have to make it as smooth as possible and as ideally close to the paraboloid shape. But then what happens is the dish surface may not be smooth. It may be having very less ups and downs, and as it gets compared to the wavelengths and all, then the losses will be more, because assume that a parallel ray is coming here. If it comes here, it has to come here. Then the same wavefront from this point has to come here and meet here at the same time. If it is a perfect paraboloid, they will meet at the same time. But if it is not, then some will meet before and some will meet afterwards, and there will be a addition and cancellation. So you will lose some of the power. So that is what happens when the dish surface is not smooth. So that efficiency also you have to measure. That is the surface smoothness efficiency, and depends on the root mean square variations of the surface of the dish. Then you have the illumination efficiency, eta illumination. This relates to the intensity variation of the signal on the dish. So what we just now explained. And this one is polarization efficiency. Polarization efficiency is something like, see, if you have a ideally, if you have a antenna which doesn't, which is very good, which receives the polarization very good. So if you are putting it in the X to receive the X polarization, then any component from Y polarization will not get into it because they are orthogonal. But actually, it doesn't happen like that. There is always some leakage of polarization, polarized power into the other antenna, and that reduces the polarization efficiency. So here are the definitions for this. The antenna efficiency, as I said, that radiation resistance by radiation resistance plus loss resistance. And the spillover efficiency, eta spillover, is actual power falling on the dish surface by total power radiated by the antenna field. So the antenna field illuminates the dish with some power, that is this total power, and actual antenna, the actual power that is falling across the dish surface. So this ratio is the spillover efficiency. And then dish leakage efficiency is power reflected by the dish surface by total power falling on the dish. Then you have surface smoothness efficiency. This is the RMS efficiency, the eta RMS. This is the actual power available at the focus of the dish by the theoretical power at the focus. If the dish surface is smooth, then theoretically you receive all power. So this is the ratio of that. Then you have the illumination efficiency. That is the total power illuminating the dish by total power required for uniform illumination at peak intensity of the field. So if you have an antenna which is having a constant antenna field with a constant illumination across it, like the ideal illumination. So that antenna will give this one, and this is the total power illuminating the dish. And polarization efficiency is actual power received by a match load on the antenna feed divided by maximum power received if the antenna had optimum polarization ability. So this ratio. See, all these ratios are always less than unity. So when you multiply them, they still go down below unity. And then when you multiply all of them, that becomes the aperture efficiency. So I have not written here. I'll go in the next page, maybe here, yes, or somewhere it will. Yeah, here it is. The aperture efficiency is equal to the product of all these efficiencies. And when you multiply the aperture efficiency with the actual aperture, physical aperture, then you get the effective aperture. That is this one. So we'll come to this. Now here you can analyze the dish geometrically. See, F is the focal length, D is the diameter, small d is the dish depth. Okay, this is the diameter. The focal length is between this point and this point. This is the focal length. And depth of the dish is between this and this. And this is the aperture surface, this dotted line. The illumination extent of the dish is measured from the focus. This is this angle, this is beta d, is the illumination extent. Now, if you, the dish diameter d can be defined as the f by d, this KEFD is the f by d ratio, or the focal length to diameter ratio, this f by d. So this diameter you can express in terms of that, the simple f by KFD from this equation you can get. And dish depth is equal to d square by 16f. All these things you can calculate geometrically. For example, the dish illumination extent you can see, that is beta d is equal to 2 tan inverse. So this you can calculate. You take this half angle, this is beta d by 2, that tan of this beta d by 2 will be equal to this divided by this, and this one you know is d by 2, and this one you know is equal to f minus d. So this is what it is. Yes. And effective aperture area will be the area of this dish multiplied by the aperture efficiency. The area of the dish is pi d square by 4 into the aperture efficiency, and that will give you the actual aperture, effective aperture area. Now, once you get the aperture area, you can calculate the effective gain. using this one. G is equal to some 4 pi A by lambda square. That is a gain relationship with lambda and all. So if you substitute all these parameters in this, from that equation you will get this is it. This is what you will get. And also the effective half power beamwidth, that is in one plane, that is equal to this some constant divided by the gain effective gain, this one, square root of that. So now we consider a paraboloid dish. Okay, this is some analysis I did in my earlier days. I have a paper on this one. If you want, you can find it here. This paper actually. This is in the Progress in Electromagnetics Research. So you can find this one if you like. But here I will try to avoid as much mathematics as possible, and I will try to explain it in a very simple way. Now we are analyzing a antenna, dish antenna. With analyzing means we want to calculate the antenna temperature, and it is not possible to calculate the antenna temperature for every instant of time because it keeps moving. So we consider one case when it is pointing to the zenith. At that time, what should be the antenna temperature? We assume that the source is at the zenith. At that position, we will do that one. Here, this is the zenith direction. So you can divide this these angles in different. So this is the illumination extent, beta D. You know this one. Your antenna feed has to be here. This is the focus. This is the spillover extent. This portion of the antenna feed illumination will go out and fall on the ground. It cannot, of course, this line will not go, but anything it will at some distance, somewhere here or there, it will fall. So I am considering this much area of this much area will be towards the ground, and this angle will be same as this angle. Beta S1 is equal to beta S2, and theta we measure in this along this. This is theta. So betas are actually thetas in some less. I mean, it varies in the same direction. This now zenith is theta is equal to 0, and the upper portion of the illumination comes from the sky. So anything above this, in this direction, this direction, this direction, or all, it will come from the sky. And also there is a source here, so something will come from the source and also from the sky. So the description says, consider a paraboloid dish is pointed to an astronomical radio source towards the zenith. Let the source be randomly polarized. We assume the polarization efficiency to be 1. Contribution to the antenna temperature are from the source, spillover, sky, and leakage through the mesh of the dish. Considering the feed to be cylindrically symmetric around the zenith, we may define. Okay, well, what I am saying is that these angles you can think that it is this in one plane. You have seen this one, it is cylindrically symmetric. So it is symmetric with the dish. So in any direction, I think I'm not able to say this in any language, but I think you can understand that around this axis, the dish is symmetric, and all these angles are also, I am assuming it to be symmetric along this axis. So that is why it is called cylindrically symmetric around the z axis. So if I just take this angle and multiply it by 2 pi, so then I will get a solid angle, because I know that this angle is everywhere along around this z axis. So the definitions are okay. Dish illumination extent is beta D. This is the illumination extent. Ground spillover, that is beta S1 plus beta S2. Then sky angle is the beta sky. So this angle. This angle is beta sky. And beam solid angle of the dish, this is for the dish. So this is omega dish is equal to effective half power beam width in both directions. The product of that is theta effective HP square. Now, if Pn be the normalized feed power pattern on the plane at phi is equal to phi naught. Well, Pn, if you remember, that is the normalized radiation power pattern. It has a maximum value of unity, and other places are less than that. It's a function of two angles. It will be in both. So here again, this is the same diagram, and this is the in earlier lectures I have explained this one, that this area is equal to sin theta d phi, whereas this one is sin theta d phi, and this angle is d theta. So if you want to, we calculate a generic angle. Generic angle means if I take an angle somewhere between this and this, I will consider it as theta 1 and theta 2, or if, on the right hand side if you see, theta is equal to 0 to pi. In this range, if I take any angle, for example, one line here and one line here, if I want to calculate the solid angle, I will integrate it over 2 pi and also integrate between this theta 1 to theta 2. That is what it is shown here. So if I have a to calculate it between 1 and 2, omega 1 and 2, you just integrate it from 0 to 2 pi, and then you have the normalized antenna pattern, and then sin theta d phi from here, and you integrate between theta 1 and theta 2. So you get simplifying, because this will be 0 to 2 pi means it will be 2 pi, and then this is what you will get. So we shall use this generic integral to calculate the various solid angles next. So this is how I have simplified the mathematics here, but we are considering it more of an ideal kind. So from here, if you see the effective beam solid angle of the feed facing the sky, including the side lobes and back lobes, are given as. So the sky angle, or here it is, this beta sky, we find out what is the omega sky from this. So you just from this expression you can find. And find out means, if you see this diagram, this is the phi. Phi will vary from 0 to 2 pi. It will go like this. So phi is equal to 0 means it is x-axis, xz plane. Xz plane will be phi is equal to 0, and phi is equal to 90 degrees if you say, then this will be yz axis. Phi is equal to 90 degrees. So for our case, we have considered that phi 0 is the plane of this paper. This is the plane of this paper, and we are considering it on this one. So effective beam solid angle of the feed illuminating the dish will be this omega d. So this will be, again, you have to integrate this. You have simply set the limits of this integration here. You just change it, and the expression remains same, and you just multiply by 2 pi. And also these two are same. This angle and this angle are same. So you can write it as total spillover divided by 2. So effective beam solid angle of the feed causing spillover will be this one. So you have just integrating it from the only the choice of integration limits you are setting, and rest are actually same if you see that. So in the same way, you calculate for all of these things, and then this is the last one, I think. Yeah, this expression is this one. Okay. Now let the source be randomly polarized. So we also assume that polarization efficiency is equal to 1. Temperature contribution to the antenna system from the dish alone. Okay. Now we have to calculate what is the antenna temperature from the dish alone. So this will be given as these various efficiencies, mesh and RMS, into this omega S, into the average temperature of the source. That is the source actually will be subtending some solid angle. So we assume that within that solid angle, what is the average temperature of the source? That is this T source. So omega S is the extent of the source. So extent of the source into the average temperature of the source into these efficiencies will be the contribution from the source alone. And then the rest will come from the sky. That is the dish, omega dish minus this omega S. You have to subtract it because that area will be hidden by the source. So that area you are subtracting it into the temperature of the sky. So that should be the temperature of the dish radiation pattern. Here it says that omega S is the angle subtended by the source, and the mean temperature of the source omega S is T source. Now you see the overall antenna temperature TA is a result of contribution from the source, spillover, sky, and leakage through the dish. We talked about this, and the temperature contributions can be subdivided into 3 groups from the sky. Okay, now we further divide it into the different categories, and this is now we are just talking about the left out things, and when we add this one with this one, we get the total what we want actually. So from the sky, we call this as this pickup from the sky pickup, and this is ground pickup, and due to mesh leakage. So antenna temperature will be this is basically because of the radiation pattern formed by the dish, and this is because of the other properties of the dish. So it has to be a addition of these two. So here you add these 3 with the antenna efficiencies and this one, where we define that T sky pickup is equal to the solid angle of the sky into all these things we have calculated, and ground leakage is equal to this one 1 minus eta mesh. So you may take some time to see the slides, and if you have any doubts, you ask me. It may not be possible to explain everything here, but I think I have tried my best to explain it logically. And if you want to see more details, you can see that paper where you will get more, and it contains something more also about GMRT. Also, I have done some analysis and put up there. Okay. So reduced aperture illumination. Although intensity of feed pattern is less across the spillover, it is reasonably higher than the side lobes. It can pick up large noise from the ground. So the solution is to reduce the feed spillover by narrowing the main lobe. It is known as reduced aperture illumination. So what you will do is you know that something is leaking over this, so you can actually reduce the width of this main lobe, so it will come inside. But then the drawbacks are it will reduce the antenna illumination efficiency, because this portion which is now coming across outside, we are trying to put it inside the dish by narrowing down. If you narrow it down, you know that this is very less power, and so the illumination of the dish will be reduced. So this will effectively reduce the aperture efficiency. The dish coordinates keep changing with time. As it moves away from the zenith, the ground contribution reduces on one side and increases on the other side. Okay, if this is a dish now, you see that this portion, this angle will be the ground contribution, this angle will be the ground contribution. If you change its position, this more of this will be coming on this side, whereas this angle towards the ground will reduce. That is what it says. And these are not well balanced. As it moves away from the ground, okay, but the dish illumination by the feed remains constant. Whatever may be the position, you will see the illumination from the feed to the dish will be same. But these things will keep on changing, the side things, contributions from the ground, sky and all, they will keep on changing. but illumination of the dish by the field will remain same. The mesh efficiency must be kept close to unity for this purpose. What it means is that there is if the mesh efficiency is less than unity, so you will have a leakage through this mesh. So at different angles of the dish, you will receive ground contributions through this leakage. You will the antenna temperature will change with the ground contributions through this leakage. So it is better that you make this one opaque as possible. Don't let it be transparent, so that it picks up the ground temperature. And what happens in practical cases is that I don't know if people have done that experiment. Maybe people have done here also. That is, if you change the pointing of the antenna, you will have a change in the antenna temperature. You will see the system noise and all. They will be changing due to its position. Apart from the, I am not considering if there is any source. If there is no source, if the sky is cold sky, but the position of the antenna changes, so you will see the temperature of the system will also change. So that is because of all of these effects, because these angles will be looking into different places, and also this leakage contributions, and all of this will play a big role in that one. Now we go for how we design the single dish radio telescopes. If you want to design a single dish radio telescope, you should know what is the size of the source that you want to do. Here are the design specifications. First, you have to know the angular size of the object. That is the size and above you can see by this telescope. Then you should have a minimum brightness of the source which you want to make your radio telescope sensitive. Below this brightness, it will not be able to receive. So that is that one. Then you also should know the sky brightness, this cold sky brightness, and then frequency or wavelength for which you are designing. The dish has to be designed for some particular frequency band, and frequency and also the bandwidth. So these 5 simple steps will tell you whether your design will succeed or not. First is that you find the minimum diameter D dash of a cent% efficient telescope. So what I mean by this is you have to use the Rayleigh criterion, because you want to use this angular, you have to resolve this angular size, this much sized object. So first you have to use the Rayleigh criterion and determine what is the diameter of the dish. So that is given by this formula. And this alpha s is the extent of the source in radians. So you calculate the diameter of the dish. Now calculate D with aperture efficiency between 0.4 and 0.5. So you can calculate it, this diameter from this diameter, what you got, using this aperture efficiency. Now what is the logic here? The logic here is, see, if you have a telescope of this diameter, then only it can resolve this one. If you have a telescope with a larger diameter also, it will be able to resolve this source, but not smaller than this. So when you are, but you also know that it will not receive the amount of power what you want. So you have to use the correct shape of the dish. So you will increase this one by multiplying it by the aperture efficiency. So you get a bigger diameter. So now you are correcting the power what you will receive from the dish. Now you are calculating the aperture area, effective aperture area. So these formulas you can understand. This is the pi d square by 4, that is the area of the dish, into the aperture efficiency is the effective area. And now you've got to connect this antenna to a receiver. Now a fairly good receiver has a temperature of between 35 and 55 Kelvin. So I don't know what is GMRT's average temperature will be something around 35 K. That's what I know. So 35 K for, yeah, I think that is the average temperature across all this. So using that, this can be the LNA temperature also, because LNA plays the that actually decides most of the receiver temperature. So now you calculate the system temperature. System temperature is equal to antenna temperature plus receiver temperature. Note that this antenna temperature is the cold sky antenna temperature. That is when your antenna is pointed towards a cold sky. So when you go to a hot object, then this will increase, and if your and this entire thing will increase, and you will be able to see a change in the system temperature. So this is your system temperature, and then you have to calculate the incremental temperature that I talked in the last class, last few classes back. Last class only, I think I talked about this before polarization. Basics of radio telescopes. So this you can simply this incremental temperature is the difference between these two. This is the source temperature minus the sky temperature. And the design is likely to succeed only if delta T emerges as the positive quantity. So your incremental temperature should be positive. Then only your design will succeed. And also in other cases also it may succeed because in some other cases, not all, because we are not using the integration here. We are just simply trying to see the noise, instantaneous noise coming from a radio telescope. If we integrate it, we can still further increase the sensitivity of the telescope. So this is not this is left out there. We are just trying to see by on hand, on pen and paper. You can calculate this, and you can tell, yeah, my system will work. It will be able to receive that one. But further things, actual system temperatures and all that, those things we will see in the receivers of radio astronomy, that I will be talking in another couple of lectures from now. Okay. Now this is something it talks about different antenna feeds and all. So I'll just read it. It's not very it's trivial. Several types of antenna feeds are available today. Each has its own advantage and disadvantages in respect of gain, bandwidth, efficiency, and side lobes, etc. We begin with the simple dipole feed for creating a background of understanding the concepts. Then we move out to ultra-wideband antenna feeds, since they are more promising for future ultra-wideband technology of radio telescopes. Finally, we discuss about horn antennas, and these are listed below. What we will discuss here is about cross dipole antenna feed, log periodic dipole arrays, non-planar ultra-wideband log periodic antenna feeds, planar log periodic ultra-wideband antenna feeds, horn antenna feeds. So I will just give the guidelines for designing these antennas, how you design them. Why don't you have the tea? Not tea. You can take. So cross dipole antenna feed. This is one of the most primitive kind of things that were tried in earlier days, but today also it is effective. Only thing is that instead of a simple feed, like a simple cross, we have a plate at the back of the cross, just to gain double the gain of that one. That is, the main lobe will increase twice, and so will happen to the all other lobes. So here is a dipole. You can see the pattern of 8 here. So if you have a reflector around this place, which will be at lambda by 4, then this portion will be reflected back and overlap this one. So effectively this will have a pattern like this, and on this side this will not have. So if you place two such, this type of feed we are also using in JMRT. If you have a cross dipole like this for picking up two polarizations, and you have something at the back, so that is good enough for limited bandwidth reception. So I'll just read it. A dipole cross is mounted at the focus of the paraboloid dish. This is the radiation pattern of the red dipole, and this is the radiation pattern of the blue dipole, and this is the combined radiation pattern of the. Okay. So disadvantages are narrow beam width, large back lobes, and poor directivity. The back lobe may be reduced by using a reflector as the back, as I just now said, that how you do that one. But most of the advantages of using a dish are spoiled if dipole feed is used. Okay, so here we go for designing of log periodic antennas. A log periodic antenna is a ultra wideband antenna. Now you know the bandwidth of a dipole is very narrow, and if you increase the thickness of the dipole to some extent, to some portion, you will get increase in the bandwidth. But that also has got some limitations. You cannot do it as much as you want. So actually, these dipole antennas are considered to be narrowband antennas. But if you stack up several such antennas of different frequency bands, maybe you will be able to create a wideband antenna. So in this diagram, you can see that there are several such antennas, each for different bandwidths, and they are somehow connected. They are connected in a crisscross fashion. That is, they are connected out of phase by 180 degrees. This is the connection you have to use for a log periodic dipole array. And you see they are placed over an angle alpha. If you change this angle, the length of the dipole array will also change, but that will give you an advantage that you will have more gain. So if you want to increase the gain of the antenna, you have to elongate this one. Also, you can see that this thickness of these dipoles are somewhat proportional. So you see this one is thicker than this one, and this one is thicker than this one. This one is thicker than this one, and so on. So the percentage bandwidth for all of them are maintained. This is the longest element and this is the shortest element. The longest element will define the lowest frequency, and the shortest element will define the highest frequency. This is the source. Now the length Ln, spacing Dn, and thickness delta n of the dipoles increases with distance starting from the smallest dipole. N is the number of dipole elements. The ratio of adjacent elements, this is known as tau. So you have to know these two things. One is this tau and another is space factor sigma. So these two are used for designing log periodic antennas, and this is symmetric from this point. All of these things are symmetric from this point. From this point you see this is Rn, and this is Rn plus 1 for the n plus 1 dipole. This is for nth dipole. So this ratio Rn divided by Rn plus 1 is same irrespective of what is the value of n. And then that is going to be the same for this length, this Ln divided by Ln plus 1. So for any, this ratio is same. And this is again equal to the thickness ratio irrespective of n. So spacing factor sigma is equal to, we define this one as this, and tau we define like this. For d is equal to, dn is equal to Rn minus 1 minus Rn. So this distance, this is dn minus 1. So from this geometry you can see what are the descriptions I have made. Apex angle alpha is equal to, again, the geometrical relationship 1 minus tau by 4 sigma. Also tan alpha by 2 is equal to this, and so on. So you also have a set of design curves that you will see in the textbook. This set of design curves gives you optimum value of choosing the number of elements in the antenna. For example, you may design a log periodic antenna with more number of dipoles or less number of dipoles, but they have the same bandwidth and say have the same gain, let us say. Instead of that, if you use these optimized curves, you will be able to design it using the minimum number of dipoles. So that is what this has got the significance. You can see these curves. This is, one side it is the scale factor tau and another side is the spacing factor sigma. Now these curves will give you, these are the gains of the antennas, gain curves actually. And this is for Z0 is equal to 100 ohms. I have not explained Z0, I will explain it later. Here it is given, I will tell you that. So for different gain curves, you have to select a line on this one, this straight line. You must be on the straight line. If you want to make an antenna of 7 dBi, you must be at this point, and you have to get the value of tau, and correspondingly you have to give the value of sigma. That is for your optimized design. Now the steps involved are: select the design curve based on the required gain. Dotted line gives optimum values of sigma. Calculate length of the smallest dipole L1, that is from the highest frequency. So L1 is equal to 0.5 C divided by nu max. Nu max is the highest frequency and C is the speed of light. Using L1 and sigma, calculate the length of the remaining dipoles. Calculate tau from two adjacent elements, and then you form the geometry, and that is how you can meet your bandwidth and all those things you can do from once you calculate sigma and tau. Then the characteristic impedance of the LPDI. This is equal to Z0. This is equal to ZOF, where I will tell that ZOF is equal to 100 ohms for L by delta is equal to 125. This delta is the thickness of the delta. This is the thickness of the dipole. And this is another x is equal to, you can calculate this value of x and you can substitute here, you can get. Now Z0 delta is the characteristic impedance of monopole of diameter delta when posited between the ground plate. Okay, I will explain this one. See, ground planes positioned on dotted lines. So consider that this line and this line to be having ground planes. You have to put some sheets of metal and so that you isolate this one. You have to isolate this. Put a sheet of metal here and put another sheet of metal here, and between that this dipole will be there. Now convert this dipole into a monopole, or you measure the impedance of this dipole in presence of these two, and divide by 2. That is that of a monopole. So that is that impedance, Z0 delta. And when you substitute this, you get the impedance of the LPDA. Now you have non-planar ultra-wideband log periodic antenna feed. This also I have used sometimes. I have made this one. These designs, I have done this design, so I just explain it. Here this is a planar form of log periodic antenna. So its directivity will be along this direction. Here it is. You can see it is along this direction. Now it has got two antennas, this and the one that is behind this one. That forms one pair, and this, and on this side there is another, that forms another pair. Now this will receive one polarization and this will receive another polarization. From the top you can see. So this is one part of the dipole, and this figure has been some, it has to be, there's something, actually this should be in this side, and or this should have been this side. This one is correctly put up. I have to correct this figure. Sorry. You see this one, these two. Here you see that this is half of the dipole and this is another half of the dipole. If you compare it with this diagram. See, this is half of the dipole, this is another half of the dipole. Here it is half of this and this is another half. And this one is the transmission line. This is one half of the transmission line, this is another half of the transmission line. So you see that in the transmission line you have to put it crisscross. So you have to connect it oppositely. The next dipole should be connected in the opposite way. So you see that one dipole is here, half dipole is here, whereas the other half dipole is in this direction. Then half dipole is in this direction and another half dipole is in this direction. And between these 2 points at the center, you are connecting the source. That's for one polarization, and similarly you have to do it for the other polarization. So one will be for horizontal, this is a horizontal polarization, and this is for vertical polarization. Now if you see this one, it's the same kind of relationship exists here also. Maybe 1 or 2 things we have added here. So these are the Rn and Rn plus 1 and all those things here. There is something called the width of this. So frequency of the end dipole is given as C by 4 Ln. Ln is this one. So this is actually quarter wavelength. So that is why 4 Ln. So that will give you the frequency. Where n is the number of dipoles and c is the speed of light. Ratio of the edge between edge distances between tau. Edge distance means this is the edge. These are the edges. This one is one edge. This is another edge. Between two is given by this expression, and this is less than this is the tau that we had been calculating in the other one. And also the ratio of frequencies of one dipole to another is the same as that of this dipole to this and this dipole to this and so on. That's what it gives. And again, if you incorporate all these frequencies, you can come to a single formula using the highest and lowest frequencies. Antenna impedance change from 70 ohms. Well, in this case, the textbooks have not described clearly how to get the antenna impedance. It's better to measure it, but it varies between 70 ohms for gamma is equal to 30 degrees to nearly 180 for gamma is equal to 180. Now what is gamma? Gamma is this one, and beta is actually the transmission line angle. So this also actually, when you design this one, this also has to be symmetric. So at the center, the thickness of the transmission line is 0 at this point, but it gradually bulges out. Now, if you, as I said here, in this one, see, if you increase this value of alpha, your gain will reduce. So, in this case also, this gamma defines the angle between this and its pair. In this one you can see this angle between this and this will be the angle formed between this one and its pair. So if you reduce that gamma, your directivity will increase. These are some of the prototypes of non-planar log-periodic antenna fields for integration with cryogenic amplifier. This was taken from University of California Radio Astronomy Laboratory. So you see here they have designed this one. This is a transmission line. They have used slightly modified dipoles. See, these are the dipoles. You see they are connected in just opposite directions. And its pair, this one side of the transmission line, the other side will be behind this one. Now that you know for designing the basic structure of planar planar log-periodic antennas, you can come for the other design. This one is my design actually. This is something new. I have got 2 papers on this one. You can see it in Journal of Electromagnetic Waves and Applications, published in Netherlands. At the time I did not get much support from the observatory, so I just let it out as paper. I didn't get much help from our PT, so I stopped the work. But this is my paper. I have seen that it has been quoted by many or cited by many people. So many people are using this one. This is very good for communications. At present people are using it, except that for radio astronomy you have to improve it slightly more, for which some softwares are required, and all of this I don't want to discuss here. Anyway, what I will do is I will tell you what it is actually. So this is a planar antenna. This design is nothing different from what you have from the textbook, except that this is a flat. Here you can see this on this one. Unlike this one, unlike this design is angular. If you straighten this, or if you make this angle gamma equal to 180 degrees, what you get is this one. So this is for one polarization, and this is for another polarization. And what you are doing is, if you do this kind of, if you make this kind of antenna, what you will see that the radiation pattern will be, suppose this is your this one, this is the antenna plane. So radiation pattern will be this way as well as this way, if you use this structure. So what I want is, I want to fold over the back one to the front one. So with that concept, I built this one. This I have made the step line reflector, and I place it exactly at λ/4 from each of these elements. So that's why it is called step. Later on I realized that instead of making a step, I could have made a just a planar kind of structure, and that works better than this one from the theoretical simulations I found that. So I'll just go for the description, what I have written here. The secondary reflector is optional. Boost gain at lower frequencies. This outside there is a ring. You can see this one. It's a ring. This is the secondary reflector. It actually boosts the gain at lower frequencies. Antennas can be fabricated on PCB, metallic sheet, shaped and fixed on a low epsilon R thin dielectric surface for mechanical support. To further reduce the effect of the dielectric, slots can be made in the dielectric between the diodes. This also reduces the air resistance. So for designing this, as I said that this is the planar lock-periodic antenna, and with reflector you will just get a double of this gain. So you see that this is given as the lock-periodic antenna with reflector into this factor. That's that relationship what I just now said. So consider a single polarized antenna associated with a step reflector. So here I have given the wavelength for minimum frequency, maximum frequency. I will not go much of this because everything is written here. If you want, if you are interested, you can read this one. And it's all geometrical relationships. There is nothing much. You have to find the tau and the. The basic concept is you have to make a planar lock-periodic antenna, and you have to use the reflector to flip the beam pattern on the other side. That is what is the basic concept. And this for one polarization, I have given all the formulas here, how to calculate all of this. And these are all geometrical relationships related to the dimensions of this reflector related to the antenna dimension. And finally, this is the tau relationship. And here is the experimental and theoretical values. Now this is the simulated gain of the planar lock-periodic antenna. it has got no reflector at the back. And this one is the gain when the reflector is fixed. So you can see that the gain almost doubles when you put the reflector. One is the simulated gain and another is the measured gain. One simulation is for pyramidal reflector, another is for the planar reflector. Probably I have not told you that. Pyramidal means one with the plane. See, there are two reflectors, either this straight line or a stepped line. The stepped one is the step plane reflector, and this the other one I call it a pyramidal. So you can get all the values here. So you can see that the pyramidal has a better response than that of a step response, and these are the measured values. And this is the ratio of this step length to this one. So you can see this is these are actually in dB. So this establishes this formula that GLPA will be less than LPA plus reflector and will be less than equal to 2.65 GLPA. Thank you. Simulated and measured antenna gains and gain ratios of functions of frequencies. Okay. Now we go to the horn antenna feeds. Horn antennas, I just read this introduction. Horn antennas are operated at microwave frequencies. They can form narrow beams and can operate as single aperture antenna. They are also used as antenna feed for dish antenna system. The horn antenna is flared waveguide. Basically, there are two types of horns: rectangular aperture horn, conical aperture horn. Rectangular has a rectangular aperture, whereas conical has a circular aperture. The flaring of the rectangular horn can be in E-plane or in H-plane or in both. These horns are respectively named as E-plane sectorial, H-plane sectorial, and pyramidal. Well, I will show you all of this. And excitation is in TE10 mode. Probably you may be remembering what is TE and TM and TE10, TE11, and so on when you have been studying the modes of excitation of waveguides. So here we use the TE10 mode, that is the simplest one, and most of the designs use this one. So that makes a very efficient way of using a rectangular waveguide in TE10 mode. Then pyramidal horns are popular since beam narrowing is possible in both directions. Well, E-plane and H-plane do beam narrowing in one dimension. The combination of this is the pyramidal, and it does it in both directions, that you will see. We show the design equations for pyramidal horn, which are based on the design equations of H-plane and E-plane sectoral horns. Okay, so this is your waveguide, this portion, this one. The waves come from this side and enter into the horn. Horn is this area. You can see that this is the illumination intensity, or at any instant of time, not illumination intensity, electric field intensity, at any instant of time entering into the waveguide. So TE10 mode, you see this one has to be lambda by 2. This dimension, one of these is called A, another is called B. I think you may be remembering those things. You refer to your macro, not going into much details. So the electric field will be directed along this direction, and a magnetic will be in this direction. This is the TE10 mode. What we have done is we have just flared out the waveguide. Now you see the thickness is maintained in this dimension, whereas the flaring is in this dimension. So this is called H-plane sectoral horn, because you are expanding it in the H-plane. Similarly, you have a E-plane sectoral horn, where you are flaring it in this direction. This one, this width is fixed. This one, this width is equal to this width. So this is called the E-plane sectoral horn. And then this is a pyramidal horn, where you have flared it in both directions. That is, you have flared in E as well as in H. And this is a conical horn, where you simply flare it out symmetrically around this axis. So if you see the design equations for this, so the E-plane sectoral horn, you see the E-plane sectoral horn means we are expanding it along this, clearing it along this direction, nothing going on this direction. So from this you can find the geometry. This angle is called alpha E, and from this to this is the LE, and this distance is the RE. And this output, this distance is actually B. So from this geometrical diagram you can actually relate this. Alpha E is equal to, you can find from this tan relationship, and RE also you can find from this. So the electric field lies parallel to the y-axis. Its intensity varies along x-axis. It is expressed as this. This is the expression for the electric field, which actually lies parallel to the y-axis. I am considering y-axis is in this direction. So for a flaring in the E-plane, you get this equation for the EAY. Now when you have a flaring in the other direction, you get similar kind of equations, and you get the equation EAY is equal to this. So I don't have to explain much here. This is the same thing, and this is the geometry on this flaring side, and from this you derive all these three things, and finally the electric field is given as a function of you can see this. Now what we want is we want for a pyramidal horn. What happens is we have to take the both of this, and we have to find a way to combine this. The pyramidal horn is composed of E-plane and H-plane sectoral horns. We obtain their respective electric field equations as you can get this electric field equations. You can see that these are the two that we derived, we got from here. We have not derived, they are just, I just put it here. So from the above two equations, we may write the electric field EAY of the pyramidal horn as. Now you just try to combine them and put it into one equation, and this is what you get. And once you get this one, then you can also find the directivity. G is equal to 4 pi A by lambda square, but I think everybody knows by this time. And this is equal to 4 pi by lambda square into the area of the horn, that is this one, into efficiency, antenna aperture efficiency. So this is something G, I don't know how it came here. This I can witness some mistake. No. A into B is the area. Sorry, this I myself confused myself. So this is A, this is B. So this is the area. This whole thing is the area into the aperture efficiency. So once you get directivity, where is okay, efficiency? Okay, for good designs, aperture efficiency lies between 0.5 to 0.7. For horn antennas, this is slightly better than that of the dish antennas, where you have aperture efficiency less than 0.5. Okay. Now we go to the more of a mathematical kind of thing. I have tried to simplify the mathematics as much as possible. I have taken out main equations and I have tried to find it how to relate them. So we will not visit much of the maths here, but if you want in details, you can read my book. So there you can see what I have done. Okay. The spatial far field pattern of an antenna is proportional to the Fourier transform of the frequency field pattern at the antenna aperture. This I have been talking before also. I gave you in the beginning lecture that the far field pattern of an antenna, that is related to the near field pattern with a Fourier transform and also function of direction cosines. So that is what it says actually. The electric field EAY, we consider an aperture here. Now we aperture in the XY plane. This is the XY plane. here you see there is a aperture here of an antenna, and along this sphere is at a very large distance, whose radius is r. You observe the far field because of this aperture. Now electric field direction, we are putting it along y-axis. That is why it is called EAY. We have put it here in this aperture. And at this point you will get two vectors perpendicular to each other. One will be E theta. E theta will be varying along this perpendicular tangential to this one. And E phi will again be perpendicular to this tangential E theta at this point. So pointing vector will be this cross this one, that will be the pointing vector. So I have just taken out the expressions. So you see that this E theta we are calculating from, we want to calculate it from this one, which is actually some constant, let us say this as a fixed term, let us say for the time being, into the electric field EAY with the Fourier transform of this, and the Fourier transforms are as a are calculated with the direction cosines. So sin theta cos phi, if you see that one, this r sin theta will be the projection here of r. Cos phi will bring it here. So projection is along this one, this is x. And r sin theta sin phi will be this direction cosine projected here and in this direction. So you see that these are the direction cosines for this point. So then you can see the integral is it turns out to be a Fourier transform. And beta is the propagation constant or wave number. In some places in physics they call it wave number. So and this portion, this phi determines the orientation of the electric field. So if you want to calculate along this this axis, what you will get, sin phi will be 0 here, because in this direction you will see that phi will become 0. So you won't get this one. So E theta will vanish. Okay. So for E theta you have this expression, and E phi you have this expression. And now we calculate it for a rectangular aperture. So this is a rectangular aperture. For example, you can check a waveguide, the front side of it, A and B. A is this one, I think B is this one. I think that's how they say it. And assume that the aperture plane behaves like a perfect magnetic conductor. So we are considering that this area to be perfect magnetic conductor, PMC. And the electric field, we are assuming it along this axis. The electric field will be along this axis. And we assume that the electric field is same in all places of this one. So that is why it is called the uniform rectangular aperture. Now from this we want to see how the far field looks like. That's what we want to see. And we will try to use this this expression to find that one. So if you just modify that these relationships for this geometry, what you will get is, using the general equations with the limits of integration set to the aperture size. So you are now setting the limits to the aperture size for the integration. And this is minus Lx by 2, this is minus Lx by 2 to Lx by 2. And this is the direction cosine component. And again the other one is from here to here, that you are setting it, and this is the direction cosine component. And you are integrating it. And finally what you get is something into a sinc function. So you see this is a sinc function, this sin A by A or something like that. It is a sinc function. So sinc function, you know that it will be having many ripples, and these ripples in this case will be the side lobe. The major lobe will be at the center, and there will be side lobes when you plot this one. And actually you can define this direction cosine components as u and v. If you remember this uv, if you remember the UV-W coordinates what I was talking about, they are related to your antenna aperture using this. That is what it is. Now, for similarly, we obtain the E phi component as shown below. So using the same relationship, you use the integration restricted from here to here and from here to here, and all those things set up. What you get is you again find a variation with a sinc function, one here, one here. So two sinc functions are coming, as you see. This I didn't say last time. See, there are two sinc functions here as well as here. One for the x-axis, one for the y-axis. One for this and one for this. That is why there are two are coming. These sinc functions generates the side lobes. I said now. The peaks of E theta and E phi depend on Lx and Ly and is directed along the z-axis. At phi is equal to 0, phi sin theta is equal to this. Rather than reading it here, I will just show you something after this. Okay, I'll just finish this reading. Similarly, for this vanish as this. What it means is that these particular values, this E theta and E phi will vanish. And for these conditions, as Lx is much greater than lambda, the main lobe, okay. So what it means is that when you are increasing the size of the aperture, if you increase this dimension and or this dimension, or you increase both, you will increase the dimension of the aperture. When you do that one, this has to be compared to the wavelength. When you do that one, what you get is the main beam narrows down. So you have a more directive here. So if you have a larger aperture, you will have a very narrow beam, or the main beam will be very narrow. Okay, I'll just read it. It's nothing much here. The sin phi and cos phi appear in E theta and E phi since electric field is polarized. For unpolarized wave, yeah, this is very important. For unpolarized wave, these factors can be unity. Thus, the normalized beam pattern Pn can be expressed as. So you are simply re-expressing it here, and this is this beta Lx by 2 kx, and you are just defining here. And beam solid angle. If you remember the description of beam solid angle, as I said in the last time, this is the integration of this normalized beam pattern over the where their lobes are present, over that. Where there is no lobes, the integration will go to 0. But anyway, that is what it is. And here also you are integrating it from 0 to 2 pi. This is pi, and 0 to pi, this is theta. And you are integrating it. And when you integrate it, you get lambda squared divided by Lx by Ly. It's a very simple relationship. So you see the beam solid angle is directly is related to the aperture dimensions. This is Lx and Ly. And also it is related to the lambda square or the wavelength. And once you know this one, you can also find out the directivity. This is 4 pi by omega A. From the radiation intensity expression, you can, I have written that one last time, that G is equal to 4 pi by A. And then you can just simply substitute this and you will get this one. Substitute from here. So you can calculate the directivity. So these are the final expressions for this rectangular aperture. And now you see the plots. So this is at the phi is equal to pi by 2. Phi is equal to pi by 2, you can see from this diagram. So this is phi. When phi is equal to pi by 2, then you have this YZ plane in this. And when phi is equal to 0, you will have this XZ plane. So in YZ plane, your radiation pattern will be something like this one, this, like this. It will be like this. Okay. Now that is what I have done in rectangular coordinates, so it doesn't look more realistic. So I have taken rectangular coordinates. So this is your theta. So theta varies in this direction, and at in YZ plane where phi is equal to pi by 2. This is when you are uniformly illuminating the rectangular aperture. And in the other plane where phi is equal to 0, that is XZ plane, here, you see that you get more of side lobes. These are the side lobes. These are side lobes. And this is the main lobe. The main lobe is pointed towards the Z direction. Now you have a tapering. Tapering illumination is something slightly different. This one, if you see this one, if you consider this as the aperture, for example, of the waveguide, you can see that the electric field reduces as it goes to the ends, but it is maximum in the center. So this can be called as a tapered illumination of this area. Whereas uniform illumination means whatever electric field you measure here is the same as you measure here. Okay. Before that, you see this diagram. This is uniform. So electric field here is same as electric field here, is same as electric field here. But here in this diagram, the electric field is less here, is 0 here, and maximum here. So this is called tapering. You have tapered at the edges. So this has got some advantages over the uniform illumination, in that discontinuity generating a lot of side lobes and all will be reduced in this case. And that is why they do the tapering. Tapering is done for that. Now here again you have a same aperture of minus Lx by 2 to x by 2, or Lx Ly is the aperture area of this one, and electric field EAY is directed along y-axis. This is the y-axis along which EAY is directed. The electric field variations across the x-axis is given as EAY is equal to E naught cos beta lambda by 4Lx. You can see this one, and this is the expression for this variation, the mathematical representation of that. This is a cosine variation. So this cos of along the direction of x, the cos of x, and these are the proportionality constants you have derived from the aperture. And this is equal to half of this, where E naught is the peak intensity. These kind of electric field variations can be observed in open-ended waveguides in TE10 mode. At x is equal to 0, the electric field intensity is maximum, and it is minimum at x is equal to L by 2. This is about the variation it is talking about. So now, when we derive the far field patterns, far field expressions for E theta and D phi, you get these expressions you will get. So you can use that first equation, and you can change the limits of integration, and you can change the excitation with the cosine, and what you get will be these will be the final expressions you will get. And these constants, this E1 and U2, are described here, and U and V is the sin theta, sin phi. These are the direction cosine components. When you plot them for in the YZ plane, you get something like this. For Lx is equal to 20 lambda, I have selected the length of the aperture. It is same for what I showed in the previous case. Ly is 10 lambda. For that type of rectangular aperture, this is what you get. And you get along this axis also in the XZ plane. So now you have to notice one thing in the previous diagram also and this diagram. See, in the XZ plane, here you see the number of side lobes are more. In the YZ plane, the number of side lobes are less. This is because you have different dimensions on different axis. So Lx is 20 lambda. So the x-axis length is more. So in the x-axis, xz plane, you will get more side lobes and they are much more suppressed because the dimension of the aperture is increasing in the x. If you had done that here also, then also you would have got this. So you would prefer this one. So that means when you are increasing the dimension of the aperture, you will be increasing the number of lobes. That's okay. But what will happen is the side lobes will be suppressed more, unlike here. Now we compare both of this, the illumination with uniform illumination and cosine tapered illumination. So this is your aperture and here is your illumination, different illumination. And finally you see that the electric fields of this. See, these dotted lines are the cosine lines. They are in red, but this overlapping has created a peculiar color. And this blue one is the uniform illumination. So in this one you see there is no much difference. In the in the YZ plane there is no much difference. But here if you see in the XZ plane, you see a lot of differences here. See, these are in dB. So so that means this can be something around 4 or 5 dB, something like that, maybe something like that. 2 to 3 dB it may be. It may not be more than that. Okay. So definitely what I mean to say is the cosine illumination has definitely changed the side lobes, whereas the main lobe you can see is it's normalized, so we have kept it here, but the ratio of main lobe to side lobe is more for a cosine illumination and less for a uniform illumination. Okay. We have seen rectangular aperture. Now we will try to see what happens if we have a circular aperture. For a circular aperture, you take a, this is your x, y, z coordinate. You take a circle. This is a aperture, and this rho dash is starts from 0 to the edge of this aperture. This describes the aperture, any point on this aperture. This is defined by this radial radial rho dash. You take a small area here. The area is ds dash, and that is equal to this rho d phi. This is rho dash d phi dash. D phi dash is this small portion, and this one is your d rho. D rho, yeah, d rho. This one is d rho. So if you multiply these two, you get that is ds dash. Infinitesimal area on aperture is ds dash is equal to this much. Now, if you want to see its component along this r at this point, so you will first get the component on this axis. You just multiply this cosine of this angle. You will get down here, and then if you multiply it again with the cosine of this angle, the angle formed between this and this angle. If you multiply with the cosine of that angle, then you go on this axis. So that is what is done here. Projection of rho dash towards r. So r dash is equal to rho dash cos phi minus phi dash. So where I have considered phi, okay, this is the phi. This is phi. This plane I have considered this as the phi. So r dash is equal to rho dash cos phi dash minus phi. So this is phi and this is phi dash. So phi dash, phi minus phi dash will be this angle. So cosine of that angle will give my projection on this axis. Cosine of that, and then this angle is equal to 90 degree minus theta. This one. So when you simplify it, it comes to this. I'll just read it in case I have missed something. A circular aperture of radius A centered at the spherical coordinate system and placed in the xy plane is shown. Let the electric field Ey be directed along the x-axis. Okay. Again, this point I forgot to tell. the electric field, we are assuming it along this direction. So wherever you measure the electric field, you will see it is oriented along x-axis on this aperture. Let ds dash be the infinitesimal area on the aperture at distance rho dash subtending an angle phi dash infinitesimal and so on. Okay. So the electric field components, when you calculate it, it will come to this. Actually, you can in this. I have given it in 3 steps. Finally, if you complete this integration, what you will get, that it will come as a Bessel function of the first kind. In the earlier case, and here E theta also as is a Bessel function of first kind, and Ex also as a Bessel function of first kind. In the earlier case, you are finding it as a sinc function. So sinc function was for rectangular aperture. For circular aperture, you will have Bessel function, and they will be in the far field pattern. Since the above are as a result of circular aperture excitation, the far field variations are guided by Bessel functions of first kind. So this you should remember for circular aperture and for rectangular aperture, what may be the differences when you increase the area of that one, what happens. These are the things that you have to think about, that if you want to change the directivity, and also this should work as intuition at the back of your mind. That's what you are doing. Finally, the mathematical relations will tell you how to do it exactly. Now, we have modeled the intensity of electric field variation across the aperture in using a parabolic function P dash. So the electric field A, not P dash, rho dash. Electric field A as a function of rho dash is equal to E naught into 1 minus rho dash by A, where A is this one. That is the radius of this aperture. Okay. So if you see this function, this is the parabolic function, and you can bring any one of these curves or any other curves by changing the value of n. So that means you can model the electric field distribution in the aperture using this equation, which you can set it to rectangular uniform by this one. When you when you put n is equal to 0, when you put n is equal to 1, you will get this kind of variation, n is equal to 2, and so on. With this electric field applied, we will try to see what happens when in the far field pattern. So this is the thing you get, that E theta is equal to this. You are integrating it. This is this is that function that you are putting it here, and here again you see that depending on the type of excitation which you are choosing by selecting the value of n, you will get a expression in the far field pattern, this one. And also a first kind Bessel function will be playing here. Now, this beta A sin theta, this was there also in the sinc function in the rectangular aperture. Here in circular aperture, this will be the same thing as functions of, this will be the Bessel functions actually. Similarly, here also you get similar kind of thing. And to refresh your memory, this is your Bessel functions of first kind, J naught x, this x axis, and this is your Bessel function amplitude, J1x, J2x. So depending on n, you will get one of this, and depending on that, your far field pattern will be changing. Okay. Now we have come across this. The aperture field is related to the far field using Fourier transform relationship. If we assume aperture illumination to be unpolarized, then the relation between near field E near and far field are expressed as For unpolarized cases, in this ideal case for radio astronomy, you can see that E far of direction cosines, function of direction cosines, is equal to some scaling factor or whatever it is. Scaling factor means here this particular term. This particular term you can call that. This is this one. And E far in LM coordinates, if you remember that UVW versus LMN coordinates, which we were talking about in the earlier lectures, in the very beginning lectures, that also again can be expressed as a Fourier transform of U and V coordinates. U and V are the direction cosines. So this should be working as intuition at the back of your mind, that what will be the far field pattern looking like. See, for engineers, from after seeing the system, it should flash in your mind that what should be the type of radiation pattern from this, what I will get. You should be able to think it out. And then if you want to go for more details, you will go and use the expressions and use computers and all. Intuitively, it should immediately come to your mind by seeing the antenna, that what is happening, what should be the pattern, what should be the side lobes, and how much is this, what is the frequency. All these things should play instantaneously. You should be able to make it out. Once that thing comes, then you can do anything you like. And these are the intuitions what I am trying to build up at the back of your mind. Now you see more of this. See the function that I have generalized here. This mathematically, this is mathematical, and you can actually calculate all these things. But to a more generalized form, you can see that if you have an excitation across the aperture of this type, then what should be the Fourier transform or the far field pattern looking like? Note that there are some things which you cannot see here. There will be rings or ripples kind of things. They are actually the side lobes. This diagram is not very clear, so it doesn't show that one. Well, let us see. There are so many diagrams. So if you have the near field, the aperture excitation as E naught into A minus rho, where A is the radius of the aperture and rho is the distance within the aperture. So you see the variation is this. This is the aperture, this round one, over which this is the variation. And if you see the far field will look like this. There are side lobes here which you cannot see here. Then you have for this cosine excitation, you have this, you see the shape is different from this. This is conical. So this is like a triangle. If you cut a slice of it, you will get a triangle here. And this is cosine. So here you see, here you will get side lobes which you are not able to see. Then cosine square, the square of the cosine. For this function you will get this. Then I think I have not done it here. In this you may be able to see some side lobes here. You're able to see something, some bluish faint blue you can see here. Probably I should change the figures and give proper figures where you can see side lobes. Anyway, this is for Gaussian excitation. This is Gaussian distribution. You can kind of think. This curve varies like a Gaussian distribution, and you get what you get is again a Gaussian. See, for this case, the when your excitation is Gaussian, the output, the field pattern will also be Gaussian, and only in this case you won't get side lobes, or even if you get, it will be very small. In any other case, you will definitely get side lobes here, and this is the worst case where you have got a step-like illumination. That's the uniform illumination across the aperture, and here you will get a lot of side lobes here. I am again sorry about this because I am not able to show it here in this diagram. So these actually I simulated it on MATLAB. These are my simulations. So I got this one, but anyway I am not able to show you the. So two types of radio arrays are used in radio astronomy. We are now moving into radio arrays. One of them is called the phased array, another is the correlator array. Array means a combination of more than one antenna is an array. Phased array means when antenna outputs are combined, are phased and combined, they are called phased arrays. And correlator array, as you see, you correct the phase, multiply, and then integrate. That sort of combination is correlator. The advantages are difficulties in constructing single dish can be overcome by arrays, because if you happen to think about capturing of very large amount of signal, you have to increase the aperture size. So if you want to do that, then your single dish may be difficult to construct. You may have to make a dish of say 1 kilometer diameter, which may not be possible. So because of that, people were thinking how to overcome this, and then some ideas came out with the additive phased arrays. Additive arrays, or they are called the phased arrays. So several antennas output can be combined. Then you have got multiple, the other advantage is multiple increase in signal to noise ratio as compared to a single dish. Obviously, if you are narrowing down the beam width, you increase the gain of the antenna, and so the signal to noise ratio goes up. Increase overall directivity and resolution of the telescope. Again, with arrays, your beam width reduces, and your directivity increases. So if your beam width reduces, so your angular resolution will increase. Then with all this, you can use the effect of arc rotation to aid supersynthesis. Supersynthesis is generally used by correlator array, but on phased arrays also you can do that one. Maybe we will not talk anything about phased arrays when we talk about supersynthesis, but I can give you something which will show you how phased arrays were, in earlier days, how phased arrays were used for that. That I will talk in some future lectures from now. Now, as a note, the GMRT configures itself in correlator array when observing spectral lines and continuum radio sources. It configures itself as a phased array when observing pulsars. So these are the two modes which GMRT operates with. Now, if you want to see what a linear antenna array is, these are the symbols what I have shown here. So this is an antenna, and you have a attenuator here, and you have a phase changer. That means you can put a delay here, and you can attenuate the signal. And then the outputs from these different antennas are added here and goes to the receiver. With this, what you are aiming here is you have several such antennas placed along a line or so. This is one-dimensional array, so I will call it as in a straight line. You are putting these antennas, and you have a object at a very distant, at some angle. You can control these phases to extend the beam on right or left. Of course, within certain angle only you can do. You cannot do it for more. And also it is restricted to a single frequency or a very narrow bandwidth or so. You can do beam steering that way. So I will start by this. So there are several antennas. First, I will consider these antennas to be isotropic radiators. I derive a general expression for the antenna array factor, which is the radiation pattern of the array. That is called array factor. And then from there, for the isotropic sources, array factor is computed. After that, you can use the actual radiation patterns, just multiply it, and you get the array factor of your system. So this is the general rules that is followed here. So I'll read it in case I missed something. A linear array is shown where all antennas are placed in a line and equally spaced. The radiation pattern and other electrical characteristics of antennas are identical. The signals received by each antenna are passed through a combination of attenuator and phase shifters. The signals are then summed and fed to the receiver. Beam pattern of an antenna array formed by non-isotropic but similar point antennas is a product of the pattern of individual antenna with pattern of an array formed by replacing all antennas with isotropic antennas. That you just have to multiply the actual beam pattern with the isotropic array pattern. Now here you can see, if you have a radio source at some infinite distance from this array, these arrays are positioned such that they are separated by distance d, each one of them, and there are n such arrays counting from 1, 2, 3 to n, and the angle the source subtends with this vertical position of this array is theta. Now if you consider any two adjacent antennas, the wavefront will reach the one of these antennas first, and after the wavefront has to travel a distance of d sin theta more. It will take some time and it will reach the upper antenna. So using this you can establish a relationship between this and all, and we assume that the pattern of all of this are same. Each antenna is identical to that of the other. So I'll read it here in case I missed something. The pattern of an antenna with isotropic point antennas is also called array factor AF. So I think it is for isotropic point antenna, that is called array factor. Array factor is for when these antennas are isotropic. Yeah. Okay. Analysis of an array is done in two steps. Find the array factor by replacing the antennas with isotropic radiators and then multiply with the radiation pattern of an individual antenna. So first you have to find the array factor and then multiply with the radiation pattern of an individual antenna to get the final pattern. N stands for the number of antennas, and signal reaching the adder from nth antenna is AN e to the power J0. Okay, the wavefront first reaches this nth antenna. So we consider that the phase shift is 0 here. We assume that this is when it hits here, it hits the 0 phase, and rest of the other phases will be with respect to this 0 phase. We will find it out. So AN e to the power J0, and this is AN. Similarly, signals reaching from n-1, that is the next antenna it will hit after some time, that will be equal to AN-1 antenna, that is the antenna before this, will be hit after this one. This phase will be e to the power j beta d sin theta. The next antenna will hit and the phase will be here 2 beta d sin theta. The next will be 3 beta d sin theta, and so on. And the final one, that is the first antenna, will be hit with e to the power j n-1 beta d sin theta. And also we have assumed that the antennas are identical and magnitude contributions are same. So the magnitude of AN is equal to A1, where N stands for any antenna. N can be 1 to N, capital N. In general, the signal from the nth antenna is given as AN is equal to the same expression. You are getting it here, and this term you are simplifying it as this psi or whatever it is. I don't know. You are putting it as BD sin theta. D is the distance between the antennas, and B is equal to 2 pi by lambda. It is the wave number or propagation constant. So A1, we are assuming that all antennas have a same A1, so that we are putting it here, A1 into this. And the output of the adder, you have to just sum all of them. Let us see, I have done sum here. No, I have not done here. So if you just sum it up, yeah, here it is. The output of the adder is the array factor KAF, given as K underscore AF of theta. It's a function of theta, is equal to A1 into this. And when you simplify it, you can express it again as a sinc function. Not exactly a sinc function. It is not a sinc function. It is something. No, it's not a sinc function. See, for sinc function, this n has to be here. This n doesn't come down here, so it is not a sinc function. So when we here applied attenuation and phase shifts are 0. Okay. What I mean here is, see, attenuations and phase shifts you can put up here using these things. Here we have assumed it to be as 0 here. So normalized variation of array factor with respect to theta. This, you can see that this is the variation of array factor for the number of antenna elements n is equal to 10, and if you keep the for different 3 distances I have shown here, and here you can see that d is equal to 0.25 lambda, d is equal to 0.5 lambda, and d is equal to 1 lambda. So let us see one by one. This dark one is 0.25 lambda, this one. Then the second one you can see that 0.5 lambda is this one, and the third one is this. So the main beam, you can see that it is shrinking down. But again you see that there are several such things that are occurring on other sides. Okay, so this thing actually repeats. Each of these things repeats itself. So you can see that this particular outline, this one, you can see here. So normalized variation of array factor with respect to theta for different spacing between, okay. The type of response is sometimes called getting response. Because of this repetition, this is called getting response. Because in getting you can see that there are several lines, and here also you see that the same thing actually it comes again and again. So that is why it is called a getting response. It's just a name, nothing to do with diffraction grating. Now consider, okay, now we consider when we consider the case when the spacing is fixed. That is, you have kept d fixed, but different phase shifts and attenuations are applied to the individual isotopic radiator. So you are you are changing the phases of individual isotopic radiators. Let the phase shift applied to the nth antenna be kappa n, and the attenuation be alpha n. So okay, and when we put it in this, we get this kind of expression. I don't know whether I have given you a plot for this. I don't know. No, I have not done that one. Okay. So with with this formula, you can actually calculate for different values of alpha n and kappa n. You can calculate the array factor. This is what it is, and the ranges of alpha is because it is attenuation, so it has to be between 0 and 1, and the phase variation you can do it between 0 and 2 pi at the most. If you do it again, 2 pi is equal to same as giving a 0 phase shift. A0 is the largest amplitude of the signal out of all elements. So A0 here. So that means A0 multiplied by alpha, it will scale the attenuation, and then the phase will be multiplied by e to the power j something. This kn is playing a role here. So if the spacing between the array is not uniform, the array factor may be expressed as, so if you are again changing the distance as well, so here you are, what is this distance element? Yeah, I have substituted this particular thing, see, this one with dn sin theta. Yeah, here it is. So in this same expression will be modified by this one. So dn represents the distance between n plus 1th element and nth element. By adjusting the amplitude and phases of the elements of an array, one can control the beam pattern in a plane. Okay. Now you did for 1 dimension. For 2 dimension, what you will have is you will place the antennas in something like a matrix kind of thing, and you will do the additions in 2 dimensions, and your beam pattern you will have to be in both of these. So you will have a width of the beam. The description says beam control in 2 dimensions is possible using a 2-dimensional array as shown. Here the array factor AF is a function of both theta and phi. Minimum spacing are dm along x-axis. So this dimensions between this and 2, the distance one is dm and dn. Dm is, can you see this diagram? Yeah, n is equal to n is equal to 1, 3, something like that I have written. No, this is 3, this is 4, this is n. N is equal to 1 is the center one, where m is also equal to 1, that is the center one. M is equal to 2, m is equal to 3, dm is this, along this direction, you can see dm, and dm is here. dn is here. Okay, so these are the spacings. Now maximum elements is m along the x-axis and n along y-axis. If no attenuation or phase shift is applied to the array factor is simply you are putting it in 2 dimensions. M is equal to 1 to m, m is equal to 1 to m in this dimension, and n is equal to 1 to n. N is equal to 1 to n you are putting, where you have described these constants as this sin theta cos phi. It's the direction cosine component, and dn is again the sin theta sin phi, the direction cosine component. So if the attenuation alpha mn and phase shift kappa mn is applied, the alpha is simply mathematical modification. So I just putting the values of alpha mn and kappa mn, and what you get is this, where alpha mn should be within this limit, and this one has to be within limits of 0 to 2 pi. So you have this, now you are plotting the array factor in 2 dimensions. One is phi is equal to 0. So phi is equal to 0 means xz plane. I did not show the diagram again. I think you can remember this. You know that what is phi is equal to 0 and phi is equal to 90 degrees. So they are both orthogonal planes. So for this we have plotted this one. You can see that for the different values of dm and dn, spacing between this, they have been kept same, except that m is equal to 5 here. The number of antennas in that axis is 5, and here it is now is 10. So I'll just read this one. Normalized variation of the array factor with respect to theta in 2 orthogonal planes. YZ plane where phi is equal to 90 degree, and XZ plane where phi is equal to 0 degree, for different spacing between the isotropic radiators for m is equal to 5, n is equal to 10. This type of response is sometimes, okay, it is also a getting response, but it's in 2 dimensions. Okay, now this already you have seen in the beginning lectures. When you want to synthesize a large rectangular aperture using small apertures, what you do is you just fill that area with number of antennas here, and effectively you have got the area equal to the sum of the areas of all these aperture areas. For 4 antennas, this one is equal to 4 into AI. AI corresponds to aperture of the ith antenna. You can put phase shifts here, and you can add them to gain the difficulties of different phases between the incoming wave fronts received at different antennas. So here it is same wave fronts come at the same instant of time. So these are set to same. And the disadvantage of this is the plane of the array must be a parallel wave, must be parallel to the wave fronts, not suitable for moving source on the sky. So I have already spoken about this. And again here, this also I have already talked about, that circular aperture you can use by very small antennas, and you can put it up to form this one. And simply this is again the summation of all the apertures. Here 19 antennas are used, so 19. And tracking antenna arrays are these, where you have a shadow effect which will reduce this. All these things I have talked. The disadvantages of tracking array are the effective area of synthesized antenna decreases as the source moves to the horizon. The delay has to be constantly adjusted for a moving source. So you have to constantly adjust the delay. So these are the delay at any instant of time, you can see here. Okay, and a gating array and its response. See, I was always talking about that you have to multiply it with the radiation pattern of the individual antenna. The array factor has to be multiplied. For the isotopic antennas, you get the array factor, you multiply it with the pattern of the actual antenna. So here is it. Here this is you can see that it's a gating array formed by a antennas having a pattern like this. This is the pattern of each individual antenna. This one. And then the array factor looks like this. This is the array factor. This one. So when you multiply them, what you get is this. This will be the response of this system. You can get this provided you adjust this to this, because the delay values has to be same, then only there will be correction, then only you will get this response. If you are not adjusting this delays, you won't get this response. I mean, this response you won't get, or the array factor will not look like this. So you have to add. If you look vertically, then these delays will be same, and the array factor will be correct. If you have to look in any direction, you have to correct the array factor by providing these delays. And this is the final output. P out, you can see that this is the summation of these voltages produced by each one of them, square of it. Proportionality constant is this. Okay, we come to the end of this lecture.